It's a pleasure to be here. Thanks very much for the invitation. So I'm going to continue on the theme sort of Anne started. So I knew she was presenting before me, so I skipped all of the nature inspiration, knowing she would at least introduce many of those topics. So you'll see some of the nature inspiration. I'm going to kind of split up the talk into two parts. The first one is primarily the ice shedding stuff, very related to what Anne was talking about. And the second part is sort of going towards, I think she was kind of alluding to that towards the end, on surfaces that don't cause ice to nucleate or propagate in the first place. So the first part would be, okay, I have ice and snow. All of us deal with ice and snow. Certainly, maybe not in Ann Arbor. Certainly people here deal with ice and snow. First joke has not landed. Okay, this is going to go well. So we'll talk about, if ice and snow is going to form, how do I get rid of that? But then the second part is, can I prevent ice from forming in the first place? So this is a lot of really brilliant graduate students and postdocs who've kind of worked on this for the last several years. Particularly want to point out a couple of grad students, Kevin and Alex, who did the bulk of this work, along with Danny, and one of my collaborators, Professor Michael Thaulis from mechanical engineering. All right, so we're going to skip this introduction already, since Anne introduced to you why icing and snow formation or accretion is such a significant challenge, right? And so I want to start off with, so you'll get a very engineering type perspective. So I'm obviously an engineer. I'm in the material science and engineering program. So you'll get a very much of a application-oriented perspective, right? So how do I actually design materials to solve these challenges, right? So I have challenges with ice forming on ships, aircraft, power lines, satellite communication being altered by ice accretions. How do I actually solve this challenge? It's a huge challenge, right? So estimated market size exceeding $5 billion a year. People have been looking at it for 70 plus years. How do I solve this challenge? So of course, because it's such a significant issue, people have been studying this for many, many decades. And one of the most common ways to kind of look at how well ice sticks to a surface has been this parameter called the ice adhesion strength, and kind of referred to that as well. Imagine you have a block of ice sitting on this surface, and I start applying, let's say, a shear force. The type of force will become important later on, as we'll discuss, but let's say I have this block of ice, I apply a shear force. What is the force per unit area required to move this block of ice? That's my ice adhesion strength. And so that's been well studied, it's well documented. This is from CRREL, which is the Army's lab on snow and ice, right? So if I look at metals like aluminum and steel, typically the values are in the 1,000 kilopascals or higher. Polymers do a lot better, on the order of 2 to 300 kilopascals. But now let me kind of give the engineering perspective. Okay, if I want to prevent icing on airplane wings or power lines or wind turbines, typically people have speculated that you might be needing values below 10 kilopascals or so. We'll see how relevant that is in just a minute. But let's say if I wanted to get 10 kilopascals and my polymers are on the order of about 200 kilopascals, there's an order of magnitude difference between where we are and where we need to be able to address this challenge. And so about 6 or 7 years ago, we started working in this area with this whole idea of, okay, I need to reduce the ice adhesion strength, right? And there's been many, many different approaches, from, waxing of various surfaces to prevent adhesion of ice and snow. Skis, people may have used waxing on their skis to make it go faster, right? So wax is a good way of being able to prevent the adhesion of ice and snow. But the challenge is it's very temporary, right? So there's no durability associated with it. And so for the first few years, we developed a bunch of different surfaces. In a second, I'll summarize that work on making things that are very, very durable, polymeric or rubber-like coatings that are very, very durable. And we published a bunch of papers on that. And then as we're starting to look at this, we started to get some funding from various agencies. Particularly, we got a lot of funding from the Navy to prevent sort of the buildup of ice and snow on ships. So as ships are going through the Arctic, there's a lot of challenges associated with icing on those all sorts of surfaces associated with ships, including like the ship hull. Now, the challenge with, say, a ship hull or a wind turbine or an airplane wing is the area of these things is huge, right? So I might be on the order of 500 meters square, 1,000 meters square, 5,000 meters square. Right? So I could work really hard on reducing the ice adhesion strength. I could go to 10 kilopascal, I could go to 1 kilopascal. There's publications going down to 0.1 kilopascal. But now I multiply that with a 5,000 meter square area, suddenly the force required to shed that ice or snow is huge. Right? So I can keep working on lowering my ice adhesion strength, but I'm particularly limited by the interfacial area when I start to look at large areas. And so back in 2019, we identified a different mode of being able to shed ice, which is by crack propagation. And the difference between those can kind of be seen here. It's one of my favorite videos, kind of sort of lays down the foundation for everything. This is just PVC. It's 4 centimeters block of ice on PVC, and essentially what you saw was the block kind of sheds as one. Whereas on the same surface, if it's longer, you can actually get crack propagation at the interface. So there's a different mode of detachment on the same exact surface, same exact condition, simple polymer, PVC. All of us have seen this. Probably many of the pipes here might actually be using PVC, right? And just by changing the length scale, I can go from a failure in the strength regime, where the block kind of moves as one, to failure in the toughness regime, where you can get crack to propagate across the interface, right? So it's a different mode of detachment. What's really good here is once the crack starts, it doesn't matter if it's going to go up till here, to here, to here, to 10 meters, to 100 meters. It's the same amount of energy required. So once my ice starts cracking, or not the ice, I should say, the interface between the ice and the coating starts cracking, I can basically keep going. And so what that means is even though my area keeps increasing, the force for detachment is the same, right? So force for detachment becomes independent of area. In fact, the larger the area, the better it is, because you have a lot of weight of ice and snow that's built up. So you can use the weight of ice and snow itself to cause the detachment, as you'll see. And so here's just sort of a summarization. So we developed various parameters, both in the first case where we have strength control regime, and we identified, as I said, I'm a material scientist, so I look at material design parameters. So what can I actually do to be able to control, let's say first, the ice adhesion strength? And then we came up with different sort of relationships that allow us to do that. In these two papers, we had about 100 different coatings from basically any polymer that you can imagine, and showed how you could make that be ice-phobic, right? By making use of the softness of the material or adding different oils. Could look at many, many different combinations. We sort of go through and explain why that is. So that's sort of the first mode, when you sort of have strength controlled detachment. What about toughness controlled detachment if you have crack propagation at the interface? So we also went through and developed the different material parameters that control detachment when you have crack propagation. As it turns out, so this is sort of one of the best ways of sort of predicting the energy required for that crack propagation, is this idea of an interfacial toughness. And we go about talking or show how you can vary, let's say, the material's thickness, its hardness, the amount of oil content, to be able to get very, very low interfacial toughness materials, meaning that you have very, very low forces required to detach large pieces of ice and snow. This is sort of one of the examples. So Michigan is a great place to be able to do ice shedding work. You can test your coatings outside. This black one, I chose a black one for a reason, as you'll see. This is one of our coatings that was developed. It's a black rubber. What you'll see in just a second is about a 1 meter by 1 meter sample. What you'll see in just a second is there's a crack that starts to propagate. And this is all at -6, so just outside during the winter. And that crack just allows for self-delamination. The entire block just falls off under its own weight, right? So, and the bigger you make this block, the better it is, because the force required is still the same. If I make it even bigger, it's even easier for us to shed that ice or have sort of self-detachment. And so this was really exciting for us in being able to now develop sort of a different mode for detachment. Right? And so back then in 2019, we said, okay, if I have large areas, if I'm looking at ships and wind turbines and airplanes and car windshields, I need these things that promote crack propagation. If I have other things, maybe I'm trying to get ice out of ice cubes out of an ice tray, or preventing the attachment of small blocks of ice and snow, then maybe I need these ice-phobic materials with a very low ice adhesion strength. So there's sort of a detachment between them. Right? And that detachment kind of exists even in material design, right? So from all of these works, and you can certainly read more about them in these publications, if I was trying to develop things for the smaller areas, sort of in the strength control regime, it turned out I need polymers that are soft and thick. For the other regime, it's exactly the opposite. I need things that are hard and thin. Of course, it's exactly the opposite, right? Because nothing comes easy, right? So because now if I have a surface sitting outside, it's going to have basically structures that are small, and it's going to have structures that are large. So how do I actually make things that work across that entire spectrum? Right? Clearly, the material design is essentially the opposite: soft and thick here, hard and thin on the other end. Turns out there is something that you can do. There is a dependence. So this is my governing parameter for crack propagation, this interfacial toughness. It actually has a dependence on the ice adhesion strength. And so if I make things that are, let's say, softer or have oils within them, you can lower the ice adhesion strength enough, because there's a square dependence, that it overcomes the other two. And so if I actually make things that are soft and have oils within them, it actually works really well. Now, there will be an obvious problem with that in just a second, but let me show you how well that kind of works. So this is some of the work we did with Sandia National Lab on a DOE-funded project, where we had these soft and thin PDMS and PVC-based coatings that we put out on photovoltaic cells in Alaska for 6 months, right? Of course, if any of you have solar cells around here, right, during the winter, you're not producing anything, because it's basically, A, there's not enough sun typically, but B, a big challenge is even if there is sun, it's your solar panels are covered with snow and ice, right? And so what we showed was over a period of 6 months in Alaska, in Fairbanks, you could significantly reduce the snow accretion on the surface. The surfaces could shed ice and snow automatically, and so you could produce much more energy during the winter relative to the baseline. This, by the way, was not the best design. You can kind of see exactly why. So this was done at one of these power companies that works with DOE, and they only gave us one panel where we could coat it, right? And so you can kind of see the uncoated and coated panels are right next to each other. And so then you have this issue of bridging, right? So my snow is sort of stuck here. It kind of bridges over the coated area as well. So not the best design, but still quite convincingly showed that these things can have utility. Now for the problem, right? I told you soft and oil-filled polymers have a problem. It's durability, right? So this thing, yes, lasted for about 6 months, but it only lasted for about 6 months because it's a soft, relatively thin, it was about a 5 micron or so thickness film, right? So it's not very durable. So how do I get around that, right? Because if I'm actually going to use it for some of the examples that Anne was mentioning, right? If I'm going to put it on wind turbines, if I'm going to put it on airplane wings, if I'm going to put it on cars, these things need to be ultra durable. And so more recently, we've kind of come up with an alternate design that kind of works while maintaining the durability, has both low ice adhesion strength and low interfacial toughness. It turns out very much sort of related to many of the laminate structures that we see in nature. We started working with laminate composites. And the special thing about these laminate composites is that we have something that's very, very soft on the bottom, and then we have something that is very, very hard, a thin layer of something that's very, very hard on the top. What that does is it lowers the effective modulus of this laminate composite. So overall, the thing is relatively soft, even though the top layer is very, very hard. That provides a lot of durability. And then we can kind of show it should lower the ice adhesion strength as well as the interfacial toughness. Now, the beauty of this is you can use any material that you want as your top layer. I'm almost out, so I will finish very quickly, including things like steel. So this is actually an ice-phobic coating made out of steel, where there is basically a soft urethane and a layer of steel on top of it. And because of that layer of steel, it is ultra durable while maintaining ice adhesion strengths on the order of 25 to 50 kilopascals. So very, very low and very low interfacial toughness. You can also use very, very hard polyurethanes as a top coat, right? and kind of show how well it scales with that effective modulus, the ice adhesion strength, and interfacial toughness, essentially showing that sort of the actual experiments kind of match the predictions. Now, this is probably the most important one to kind of show. This is what's called as a rain erosion test for a coating. So if any coating is going to be used for wind turbines or aerospace, in aerospace for airplane wings, it has to pass the so-called rain erosion test. And what that means is you have 100 microns, 50 to 100 micron droplets coming in at 200 to 250 miles an hour and hitting your surface, right? And like the first coatings that we made, which we thought were the most durable coatings ever made, lasted for about 30 seconds in that test. Is just blasted completely. Once you have these steel and urethane hard coats, even after 8 hours, basically they're completely fine. There's no issue. They keep maintaining their ice adhesion strength, as well as interfacial toughness, keep shedding things. And finally, getting back to, as I was saying, this is all funded by the Navy. I don't know if we can play the video. Any way to play the video? Oh, it worked. Okay. Right. This is actually the gray stuff is an actual Navy top coat, and this is where we're at now. We can actually modify the current Navy top coat and just have things shed very, very rapidly. So very excited to have this be scaled up. We have a bunch of testing going on different skyscrapers in New York, on different ships very shortly. We'll have many, many different solar panels across the country be coated with some of these during this winter. So hopefully we should be able to get a lot more data showing the utilization of these type of coatings. Final thing that I'll mention, we've been building up a lot of different testing facilities. This is really significant, as we show in this review. How you test how well ice sticks to a surface matters, whether you're applying forces in shear, whether you're applying it in tension, whether you're applying it in mixed mode. You can get widely differing numbers for how well things stick to a surface. We show in this review, you can get basically an order of magnitude values. Basically, you can get any number that you want with any surface, right, depending on how you're testing it. And so there needs to be a facility where you can kind of test these things out in different ways. So we have facilities now built up for testing ice in various modes, as well as now snow gets even more complicated because now you have 3 potential phases rather than just a solid. You have solid, you have air, and you have liquid water. So now we've built up facilities for being able to make reproducibly the same structure of snow over and over again to be able to evaluate these. The final thing, although I'm completely out of time, to get to biomimicry. So this is what I'm hoping, was hoping to actually include a lot more results on it. This project is just starting. It's a new DARPA-funded project. It's a really cool idea. So as we kind of look at different Arctic insects and fish and frogs, these things, their blood for many of them doesn't freeze when you're down to minus 30 C, for some to minus 40 C, all the way down to minus 60 C, and the thing doesn't freeze, right? And so over the last maybe 10 years or so, a few of the antifreeze proteins have been identified, antifreeze glycolipids have been identified from these structures. The challenge is typically it's not a single antifreeze protein that's existing, it's not a single antifreeze glycolipids, it's typically mixtures, right? And then they typically also have different sugar alcohols and different sugars which can act as so-called deep eutectic systems to significantly lower the freezing point. And even though a few antifreeze proteins and glycolipids have been identified, it's not known how different of these compounds come together, what is the right ratios, and so on. And so this project by DARPA was sort of twofold. A, being able to make artificial mimics of these thousands of different natural antifreeze proteins and glycolipids and sugar alcohols. And B, being able to, in a very high throughput manner, combine them and see how it impacts icing. And so part of what we're building now is a high throughput screening setup, which in an automated manner, will be able to screen through 1,500 samples in one day. Different combinations of different molecules, being able to look through those to identify what are the best promising system, and then look at why they work the way that they do. And so there's a bunch of different facilities being built for that. So with that, let me end. Thanks certainly all the wonderful students. I have this group is now expanded even further, so it's not the most recent image, as well as funding from the Navy. So with that, thank you very much. Great.